Right, so this is going to be the work problems for Chapter 17A, and I'm going to go through them expeditiously, mainly because I want to try to keep the file size of this thing down. The last presentation that I did was about 150 megs, which is really a lot. It's okay as far as the size, as far as Canvas, but it's still a huge file. So I will be limited into how much time I can spend on each problem. So I'm going to go through these. Before I start going through the actual problems, I need to remind you again that this is going to be a PowerPoint thing, which means that every time I stop talking and hit the switch to the next slide button, then it's going to probably stop for you, which means that you'll have to click it. In other words, every time I click, you'll have to click. So it's a little annoying, and if I can figure out a way to get out of that, I'll do it. But otherwise, that's the way it is for right now. So I'm going to click now. Let's go ahead and move on to the next problem. So you'll have to click at home. You may have to keep clicking. Okay, first of all, this is just a list of the strong acids and strong bases. We've already done that. So let's go ahead and move on to the next one. And our first problem here is that we are supposed to find the pH for these different solutions. This is a weak acid, this is a weak base, this is just water. We can answer this one right here. Let me get my marker up. This one right here, we know the answer to this already. It's 7. And it's very difficult, if you haven't heard me say this before, it's very difficult to write with this little ball thing here. So I'm working on getting better at it, but I don't think it's ever going to happen. So this is a weak acid, this is a weak base, and then down at the bottom we have a buffer. A buffer solution means you've got a weak acid and its conjugate base both. So you can get a buffer solution by mixing it intentionally, or you can also wind up with a buffer solution when you're doing a titration of either a weak acid or a weak base. So it's basically after you start before the equivalence point. So for A, this is a weak acid, so what we need to do is go ahead and we have the concentration of the acid, and that's all we have. So we'll just go ahead. We don't have to do any stoichiometric calculations for this because we're not adding anything. It's just the acid, right? Same thing for B, 0.1 molar propanoate. We are not adding anything. We don't have to do any stoichiometric calculations. We can just go right to the ice table. So these are just basic weak acid problem for A, and for B, weak base. So an ice table for each. The difference will be, and you have to be careful with this, for B, you're doing weak base. This is sodium propanoate, so you don't really care about the sodium part. This is going to have a negative charge on it, this C3H5O2. So that is what you're actually going to have in the water. So you'll want to start off by adding water to that. But when you add water to a weak base and then see what happens, that is a Kb expression. So you don't want to use this Ka right here because you'll get the wrong answer. You have to convert this number 1.3 times 10 to the minus 5th to the Kb. So you want to take 1 times 10 to the minus 14th divided by 1.3 times 10 to the minus 5th to get Kb for part B. Now, one of the other problems is once I switch to the next slide, I can't go back. So that creates problems. So what we're going to see, part C is going to be that the pH is going to be 7, period. And then for D, there's a couple of different ways you could do it, but let's just look at it before we turn over here. For part D, this is going to be a buffer solution, and also the concentration of this acid and the concentration of the base are the same. So if we use, for this one, the HH equation, because it's a buffer solution, we can use the HH equation. But when we do that, you'll notice here that the concentrations of the acid is 0.1 molar and the base is 0.1 molar. So the HH equation states pH is pKa plus the log of the base over the acid. If you divide 0.1 by 0.1, in other words, the base over the acid, you get 1. And the log of 1 is 0, so that term just drops out, right? So you're left with pH equals pKa. So for this one, we're going to get pH is pKa. Now let me just take this and I've got a calculator right here, 1.3, and I'm not going to do this for every problem, but 1.3 times 10 to the minus fifth is our Ka. So I'm going to take the log of that and to get the pKa, and that is minus 4.886. So we'll flip over in just a minute and look at that. But so the Ka is 1.3 times 10 to the minus fifth, so we take the log of that, and then it would be the negative of that, so it's going to be 4.89, it looks like, which would make sense because it's going to be between 10 to the minus fifth and 10 to the minus fourth, closer to 10 to the minus fifth, so closer to 5. So it's 4.89, it looks like. So it looks like that's going to be the answer actually to part D, about 4.89. For part A, we'll have to set up an ice table, but we already know what we're going to get, right? We're going to get x squared over the initial concentration, which is 0.1. And I'm not going to try to write it out here. I would if I could just write it by hand, but to do it with this little thing right here takes too much time. So for part A, we're going to wind up with x squared over part 0.1 equals the Ka. And for part B, it'll be the same thing except that we want the Kb rather than the Ka. Now let me just, I'm not going to do this the whole show, but 1 times 10 to the minus 14th divided by this number right here, 1.3 times 10 to the minus fifth, gives me 7.7 times 10 to the minus 10th. So for part B, we'll want to use that for Kb, not this 1.3 up here times 10 to the minus fifth. So I'm going to go ahead and flip over. The answer will be here on the next slide. So for part A, we're doing the acid. Unfortunately, for this particular problem, I've got the ice tables on the next slide, and I don't really want to leave this slide until we understand what's going on. But so we're going to wind up here with the ice table, and then when we solve the ice table, we end up with x squared divided by 0.1 equals this Ka for part A. And then we just solve it for x. That's going to give us the H plus concentration. Take minus the log. So when we do that, we get x is 0.00114, and then take minus the log of the 0.00114, and that's going to give us 2.943 for our answer. So part A, 2.943. So this is just the way we've been doing these weak acid problems. For part B, again, we're going to wind up with x squared over 0.1, but this time we want to use Kb, and so I do want to just like slow down for just a second here and point out that when you're doing part B, I've got it listed over here as a salt problem, which whenever you have a salt problem, it's always going to wind up being that you don't really care about the cation, you care about the anion, which in this case is C3H5O2 minus. That is called propanoate. Remember from organic, we said that when there are 3 carbons, that's called propane, right? So if you have 3 carbons in an acid, that's propanoic acid. And when you take away the H plus from that, it's propanoate. But be sure that you understand this because this is really tricky. This is all we have, right? So in water. So all we have is water and this stuff right here. So the only thing that we can do with this is to add those 2 things together like this. And then what's going to happen? Well, the propanoate will pluck a proton off the water and reconstitute the propanoic acid here. Leaving the water is now it's going to be OH minus. But notice that this is a Kb. This is Kb expression, not Ka. So we don't want to use Ka. This is Kb. And to get the KB from this number right here, we have to divide 1 times 10 to the minus 14th by that number. And it's done here, right there. And when you do that, you get what I said before, 7.69 times 10 to the minus 10th, right? So you want to set this number right here equal to x squared divided by 0.1 and solve for x. And that's going to give you, which we'll see that when I flip the slide, but it's going to give you the concentration of the OH minus. Okay, so when you take minus the log of that, you're going to get the POH, not the pH. So again, be careful there. And I mean, again, especially on the final, you really have to watch it there, because I can't really like give you partial credit on those. All right, so once you figure out what the POH is, you already know what to do then, right? So the POH is about 5, so that means the pH should be about 14 minus 5, or it should be about 9, and it is. So I'm going to flip now to the next slide. Actually, I'm going to try doing it. Yeah, there we go. Okay, so here are the ice tables. We're starting off for A and for B here with 0.1. And then for both of them, we end up with x times x over the 0.1. Both of them, it's the same. The only difference is you set the top one equal to Ka, and you set this one equal to Kb. So Kb equals x squared over 0.1. And then this is what you should get for your buffer solution. You're starting off with the propanoate at 0.1. Okay. Now they're going to now ask us which one of these has the greater percent dissociation. So it turns out that this one up here will have a much larger x, whereas this one will have a much smaller x. So when you divide x here by your original concentration here, you're going to get a larger number for this one than for this one down here. So the one here in part D is going to give you a very small number, and that's because this is a buffer solution. So that means that this one, this part D, is going to change its pH much, much less than this one. All right, so let's go ahead and take a look at it. So the next two problems are going to deal with that. So I'm going to click. So compare the percent dissociation of D and A, of D and A. Well, A was fairly large, and D was very small. And let's click to the next slide here. So for A, it was 0.00114, which is what we got for X, divided by the original concentration here, which is 0.1, and we get 1.14%. Whereas for part D, we solved it for X, and we got 0.00013. That's a much smaller number. And then when we divide that, we got 1.3 times 10 to the minus 5th. And when we divided that by 0.1, which was the original concentration, we get 0.00013, or 0.013%. So that's really, really tiny. I'm going to go to the next slide. And this is still referring back to the first problem. Which of these solutions will show the least change in pH if you add an acid or a base? And obviously a buffer solution is going to change less. So, and this one is a buffer solution. So this is the one that's going to be the answer for number 3. Let's quickly go ahead and now move on, because there's a lot of stuff here. Here's the answer to that question. Let's move on. All right, next, this is a new topic. Calculate the pH of a solution that's 1 molar HNO2, 1 molar NaNO2. Okay, so first of all, we have to figure out what kind of a solution this is, what's going on. And it doesn't take a rocket scientist to figure out that this is a weak acid and this is its conjugate base. Again, we don't care about the Na. The Na doesn't have acid-base properties. It's just a placeholder. I don't know why I keep coming back to that, but anyway, I guess that I'm making my point here. All right, so this is a weak acid. It's nitrous acid, and then this is the weak conjugate base of that weak acid. It's just NO2 minus. So in order to find the pH of this, there's a couple of ways you can do it. You can go ahead and do it the long way, which means make an ice table. So you're going to be starting off for your acid here with 1 molar minus X equals 1 minus X, and then add it to water and so forth. Or you can just use the HH equation, and it turns out that that's the best way to do these. I mean, unless you just really want to do it the other way, and that's fine if you do. But usually if you're trying to get done with these, the quickest way to do it is just to use the HH equation. So that's pH equals pKa. We're given the Ka right here. It's 4 times 10 to the minus 4th. What you can do sometimes is just look at these. I mean, I don't want to spend any time on this, but this number right here is between 10 to the minus 4th and 10 to the minus 3rd, which would give you a log between 3 and 4, and it's about halfway. So I'm guessing that the pKa is going to be about 3.5. So we'll find out when we flip over. But just take the case that it is 3.5. That's going to actually be the pH, because the pH in this case will equal pKa, right? You remember this, right? Because the concentrations here are equal. They're both 1. The acid is 1, and the base is 1. So 1 over 1 is 1, log of 1 is 0. So the pH is just going to equal the pKa. So let's flip it. I'm going to go ahead and move to the next slide. And so we wind up with pH equals pKa, which I'm down at the bottom now of the slide, because when I did this a long time ago, I was going through these, some of these, I was going through them the long way, and that's fine. Some people actually learn better if they do these the long way, and that's absolutely fine. But after you've done them for a while, you'll get to the point where you'll probably, whenever you've got a buffer solution, or whenever you're doing a titration that ends up with a buffer solution, it's usually easier just to use the HH equation. So this term is just going to drop out, because it's going to be 1 over 1. Log of 1 is 0. We wind up here, I said it would be about 3.5, and it's about actually 3.4. But at least we're in the right ballpark, right? Okay, so just take minus the log of 4 times 10 to the minus 4th. That's minus the log of the Ka, which was given on the previous slide, and it's also given right here. So that's where that comes from. Just take minus the log of that, and you get about 3.4. And remember, for pHs, there's a rule: the number of sig figs in the concentration equals the number of decimal places in the pH value. All right, I'm going to click to the next slide. For all 4 of these, we're going to use the HH equation, because for all of these, we have a weak acid and its conjugate base. So for the HH equation, it's going to be that pH equals pKa plus the log of the base over the acid. And please just ignore, I've got a bunch of birds, so try not to pay any attention to them. So the base concentration over the acid. Now it turns out here that if you do all 4 of these 2 come out the same, and these 2 come out the same, because the ratio for these 2 right here, let's see, is that right? So this one's 2.5, and what I mean by that is if you divide the the 0.25 by the 0.1, you get 2.5, and then you also get that 2.5. Well, maybe I'm confusing this with another problem, but I don't think I am. Anyway, so 2.5 here. All right, well, anyway, let's just forget what I was just saying. But so just to go through these for all of them, here when you divide 0.08 by 0.2, you're going to get 0.4. When you divide 0.2 by 0.08, you're going to get 2.5, right? So that's correct. So this one right here is the same answer as this one because the ratios are the same. So what matters is the ratio, and then this one right here is the same as this one right here because the ratios are the same. So pH is pKa. Now these are acetic acid, so for acetic acid, the Ka value is going to be 1.8 times 10 to the minus fifth. And when you take the minus the log of that, you're going to get about 4.75. So, I mean, it's really slow to do this. And then you can't even read it after I do it. And there's absolutely, I mean, if you're wondering why I don't put the birds in the other room, it's because their cage is so large that I can't get it through the hallway. Okay, so 4.75. They've been asleep all day long and now they decide to wake up. The pKa would be 4.75. So this is going to be maybe the last time I try to write anything for obvious reasons. The pKa will be about 4.75. I think it's actually 4.7475. So it would be this number right here for all four of these over here. It will be this number right here plus the log of whatever the ratio. So here it would be the log of 2.5 and also here. And here it would be the log of 0.4 and also down here. Now remember, the log of a number less than 1 is going to be negative. So let's flip over. So I'm going to flip to the next slide. Notice for part A here, I did it the long way first, and then I used the HH equation here. So 4.75, and then the log of 2.5, 2.5, the log of 2.5 is 0.3979. So we just add these two things together here, and our answer is going to be 5.14. The log of this number is going to be negative here. That one right there is going to be negative because that number is less than 1. Okay, I'm going to flip. C and D are going to be done the same way, and you're actually, if you'll check back, I can't go back, but if you'll check back, this number is the same as part A, right? And this number is the same as part B. All right, so I'm going to flip to the next slide. All right, number 6, calculate the pH of a buffer solution. Okay, that indicates that we're probably going to use the HH equation again, right? So, I mean, if it's a buffer solution, we're probably going to use the HH equation, which I'm not going to write because it takes too long. The only difference here is that we have to actually figure out the concentrations of the acid, in this case the benzoic acid, and the base, which in this case is benzoate. So if you have benzoic acid and it donates a proton, then you're left with benzoate. So the only difference in those two would be that the benzoate has lost one H. Let me see if I can cover them up. I hate to do that. All right, so then what we'll have to do for both of these is divide these two masses, this one and this one, by the molar masses. Now this one, the benzoic acid, to get the molar mass, you just add the masses of these, which is straightforward. But for the sodium benzoate, you'll also have to add that mass, which is 23. You'll also lose 1 because when you go from the benzoic acid to the benzoate, you're donating a proton, so you lose a mass of 1 for that H that you donated, but you're gaining 23, which we'll see in the next slide. All right, so whatever the mass is of benzoic acid, divide 21.46 here, divide that number by whatever the mass of benzoic acid is, and then divide this number by whatever the mass of sodium benzoate is, and that gives you the number of moles, but that doesn't give you the concentration. Okay, so what we'll need to do is for both of those number of moles, we'll have to divide by 0.2 liters to get it in molarity. Once we've done that, we take whatever the concentration or molarity is of this thing right here, divided by the concentration of this one, and then take the log of that. So again, we're using HH, and then we'll also want to take minus the log of 6.4 times. Now again, here, if you'll look at this, if you want to just get a rough estimate, this is going to be between 10 to the minus 5th and 10 to the minus 4th. So if you take minus the log of that, it's going to be between 4 and 5. And again, it's about halfway. So just say 4.5. So I'm just guessing here. I'm just getting a rough estimate. I'm going to say 4.5. And I'm not going to try to write it because it takes too long. So I'm going to flip this slide. And so I immediately came down here to see if I got this right. And it's actually more like 4.2. But anyway. All right, so the pKa is 4.2 here. When we figured out what these molar masses were for the benzoic acid, it was 122 grams per mole. And for the benzoate, remember we took away 1 and added 23. So it jumps up to 144. So, I mean, just to show one of these, we divide 37.68 by 144 to get the number of moles of the benzoate. And then once we have these two numbers of moles here and here, we divide both of these numbers by 0.2 liters because that was the total volume to get the concentrations. So both of these we have to divide by 0.2 liters. So 0.176 moles divided by 0.2 liters here is 0.88 moles per liter, and then do the same thing here for the benzoate. We had 0.2612 moles, so divide that by 0.2 liters here, and we get 1.306. Okay, this one is the base, this one right here, and this one is the acid. So we want to divide this one by this one. So in other words, we want to divide 1.3 by 0.88, which is like a little less than 1.5. It's actually it's all about 1.5. It's this number right here. And then take the log of that, and it turns out the log of that number is 0.172, which we then add to the pKa here of 4.19. So 4.19 plus 0.172 gives us 4.36 for the answer. And that's all we have to do. I'm going to go ahead and click now to the next slide. All right, this one's along the same vein. Calculate the mass of the sodium acetate that must be added to 500 milliliters of 0.2 molar acetic acid to form a pH equals 5 buffer. So the HH equation says that pH equals pKa plus the log of the base over the acid. So I'll just write that out. We've got it on the next slide anyway. All right, so pKa, if this is acetic acid, is going to be about 4.75. Right, because the Ka is this, so when you take minus the log of that, you get about 4.75 plus the log. Oh, this is so frustrating. Plus the log of the base over the acid. Okay, and so let's just write this as the concentration of the base over the concentration of the acid. Okay, so let's look at what we have. First of all, they want us to figure it out so that the pH is going to be 5. So we're just going to substitute 5 here. And then for this one, we're just going to substitute the value that it is. If we take minus the log of this number up here, we get about 4.75. So what that's telling us is that if we subtract 4.75 from both sides of this equation, now this is an equation, and then we've got this other stuff over here, which I'm not going to rewrite. We've got plus log of B over A. If we subtract this value right here from both sides, we're going to get 0.25 on the left equals the log of B over A. Or if you want, and what I did in this problem was I just substituted the letter X for the log of B over A. And then the next problem is very similar to this one. And in the next problem, I didn't do that. So you can do it if you want to. In this one, when you look at the solution, you're going to see that I replaced that whole term right there with X. So I wound up with X equals 0.25. And then I replaced the X again with what it stood for, which was the log of the B over the A. Okay, so as we've done many, many times, right, the easiest way to solve a problem like this is to raise both sides of the equation to 10 to the power of that and 10 to the power of that. So let me just do that real quick. 10 raised to the power of 0.25 is 1.78 approximately. I'm rounding it off a little bit. So this is 1.78. Equals, and then remember, when we raise 10 to the power log of something, the 10 and the log cancel each other, and we're just left with B over A. It's actually concentration of B over concentration of A. Why am I not writing all of that? Because it takes too long. All right, but we know what one of these, we know from the problem statement one of these two values right here. So let's look back, and it turns out that it was actually the acetic acid that we know what the concentration is. It's 0.2 moles per liter. So this one right here, we already know what it is. It's 0.2. And that's moles per liter. So can we figure out, if we know what this is here, and if we know what this is, then can we figure out what B is? Yes. In fact, all we have to do is multiply the 1.78 times the 0.2. Okay, so when we do that, that will give us B. It will give us the concentration of B. So let me just do that. So I'm going to do this on the calculator. It's 0.356. And this is the moles per liter of the base, which is the acetate. Okay, so it's moles per liter. There we go. And then in order to get the mass, we just multiply that by whatever the mass of sodium acetate is, which we figured that out before, right, a few slides back. And I think it was 144 grams per mole, but I'm not sure about that. So whatever it was, then we would multiply the 0.356 times that, 144 or whatever. That would give us the mass of sodium acetate that would have to be added to 1 liter of the acid. But we don't want 1 liter, we only want half of that. So what we have to do for this value right here is just divide it by 2. And all of this is done for you on the next slide. And the reason we're dividing by 2 is because we're trying to make only half of a liter, not 1 liter. Okay, so anyway, let me flip. I'm going to flip now to the next slide. And we see down here that the concentration of the acid that we would need would be 0.36. I'm sorry, the concentration of the acetate would be 0.36 moles per liter. But as we just mentioned, we don't need 1 liter, we just need a half a liter. So we multiply this number by 1/2 here, and then whatever we get, the number of moles that we get here, we then have to multiply that by the molecular mass for the acetate. So this has a molecular mass of 82. So I'm not sure where I got that 144. That must have been for something else. So anyway, we multiply 1/2 times the 0.36 here, and we get 0.18 moles, which we multiply by 82. So multiplying 0.18 times 82 here, and we get 14.76 grams, and that's your answer. Moving to the next slide. This problem is basically going to be the same thing. Notice here that you're given the pH. You're supposed to figure out what the bicarbonate concentration is supposed to be. And also we're given the Ka here for carbonic acid. So what I'll do right now is I'll go ahead and figure out pKa by taking minus the log of 4.3 times 10 to the minus 7th. In other words, this number right here. And that's going to equal, so 4.3 times 10 to the minus 7th is going to give me 6.37. So the pKa here is 6.37. So when we set up our equation, it's going to be that 7.4, and I'm getting that from the problem statement because that's the pH that we're trying to get here. Okay, and that is going to equal, let me just go ahead and finish that there, pKa, which is 6.37. I know this is hard to read. Okay, plus the log of the base. So I'm just going to write plus, plus, so I can get this thing to work, and then I'll put 3 dots. Okay, so that stands for the log of the base over the acid. Okay, so what we would do is subtract 6.37 from both sides, which is actually done on the next slide. It's going to be about 1.03 or something like that, right? And that's going to equal the log of the base over the acid. Which I'll just write it this way because it's just faster. The log of the base of over the acid. Raise both sides to 10 to the power. So 10 to the 1.03, that's going to be just a little bit more than 10. And then raise this side to 10 to the power of log something. And when you do that, the 10 and the log cancel. So let me mark the 10 and then pretend that's log. And we're going to have B over A here. B over A. So it's really the same thing we did in the previous problem, right? Now, 10 to the 1.03 is going to be just a little bit more than 10. So, I mean, let's just guess. Let's just say it's 10.1. We'll see the actual answer in just a second. Equals the concentration of B over the concentration of A. But we were told one of those concentrations in the problem statement, and it was the acid. So carbonic acid concentration is 0.0012. So we can say that that equals B divided by divided by 0.0010. That's a big 2. So we can solve that obviously for B, and actually that would finish the problem, right? Because that's what they're asking for, is just the concentration. In other words, they want to know how many moles per liter. I might just point this out right now. And then also when we get to 17B, we'll need to remember this as well. There are 3 things, and I'm not even going to attempt to write them out, but concentration, solubility, concentration, and molarity all mean the same thing. So anyway, we're supposed to find the concentration of this. So all we have to do is multiply this 0.0012 times whatever this number was, about 10.1. Let's flip over, so I'm going to flip now. And it was 10.8. I'm not doing very good on my guesses today. And then we know that this was 0.0012. So again, we multiply the 0.0012 times 10.8, as it turns out. And when we do that, we get 0.01296 molar for the base, which is the bicarbonate here. And that's the end of the problem. That's all we had to figure out. So the answer, rounded to the proper number sig figs, is 0.013 moles per liter. Okay, so if you have any questions about these, don't hesitate to email. Again, remember these things I'm working on, trying to do this so that you don't have to keep clicking these all the time. And I'm also trying to figure out how to work this thing right here better. Anyway, we're not quite done. I figure we still have quite a ways to go. Let me go ahead now and flip to the next slide. All right, so this problem here, I think it's a good idea for you to go ahead and do this problem, even though you're probably not going to see it on a test. The rule here is that if they give you this kind of a problem with a list of acids, what you want to do is, if you want a buffer that has a pH of 7 for whatever reason, you want to look at your list of acids, like you've got this one, you know, I think the list is actually like 6 or 7 of them. And what you're looking for is and then they list over here on the right the pKa values for each of these acids. So what you want to do is you want to try to find the one that has the pKa that's closest to 7. And it turns out that I think it's HClO that is the correct choice here, which has like a pKa of something like 8, as I recall. So, and the other ones, and that isn't particularly close, but the other ones are even further off. Like, I think one of them is like 10 or 11, and one of them is like 4 or something. So what you do is you choose the one that's closest. So, and I can't flip to that right now, because if I do, I can't get back. So anyway, just take my word for it. So what we want to do is pick the right one, and then again go with the pH equals pKa, which I won't write it all out again, but it's pH equals pKa plus the log of the base over the acid. Okay, so what you would do then, in order to make this buffer, is you would just use the HH equation to figure out what the log of the base over the acid is. Let's just over. Okay, so I'm coming down here kind of towards the bottom. It's actually HOCl, hypochlorous acid, and that's what I said, has a Ka of 3.5 times 10 to the minus 8th. So we're going to use this value right here for the pKa. So we want to use the HH equation. pH is pKa plus the log of the base over the acid. We're going to use whatever minus the log of that is for the pKa, and then the pH is from the problem statement here. It's that 7 right there. So put the 7 right there under the pH, and then when you do minus the log of this number right here, you get 7.456. And then this, again, I did this thing where I substituted X for all of this stuff right here just to make it a little less tedious. And I get that X is minus 0.456 here. And then I put minus 4.456 equals, and then I put this back in. It equals to the log of the base over the acid. Now, for this one, what you have to do is make an assumption, which you have to basically come up with your own number for one of these. If we do this the way we've done these in the past, we raise both sides again to 10 to the power. When you raise 10 to the power of minus 0.456, you get 0.35. And when you raise 10 to the log of the base over the acid, you get the base over the acid. In other words, the concentration of the base over the concentration of the acid is 0.35. But we don't have either concentration given to us, right? So the only way that we can do this is to just make an assumption. So let's just do the easy way and assume that the concentration of that one is 1. Then that means the concentration of this one right here has to be 0.35. And so if that were the case, 0.35 divided by 1 would be 0.35, and this would be a true statement here. So let's go back to the problem statement, explain how to make a buffer that would be 1 liter of this. Well, we want the concentration to be, for the base to be 0.35 and for the acid to be 1. So we want to use 0.35 molars base. So we make up a liter solution with the concentration of the acid as 1 molar, and that's coming from right here. We decided to use 1 there, and the concentration of the base here to be 0.35 molar. In other words, you just add enough of the base so that the concentration is 0.35, and it's pretty easy to do when you have a total volume of 1 liter, as we do here. All right, let's move to the next one. Here are the values. I just want to stop for a second on this one. Here is the one that we chose. And you can see we were trying to find whatever is closest to give a pKa that would be closest to 7. So let me just do this one right here. So what I'm going to do is I'm going to type in 3.5 times 10 to the minus 8th. And then I take minus the log of that, and I get about 7.5. Okay. So when you take the pKa, it's about 7.5. You can try that on your own. And actually, it should be on the previous slide anyway. Whereas you'll notice here, all of these from here up are much lower. And then these down here are much higher. So the only real legitimate choice would have been to choose this one. Okay. Again, now for this one, I don't think you're going to see this on the test, but you should look this over at least because it's a good exercise. Next slide. All right. Consider the titration of a generic weak acid with a strong base. Gives the following titration curve. Across the bottom, we're denoting how much the volume is of the, like, NaOH we're adding or whatever it is, a strong base. So on the curve, indicate the points that correspond to the following. A, the stoichiometric equivalence point. Some books call this equivalence point. We're calling it the equivalence point, right? Some books call it the stoichiometric point. It's the equivalence point, and it's going to be, as we said in lab, where this curve right here stops increasing in slope and starts decreasing in slope. So it looks like, to me, it would be about right there, if you can see what I'm doing there. So that's called an inflection point in calculus. So it's getting steeper, it's getting more and more steep up until it gets to right there, roughly, and then it starts to become less steep. You see what I'm saying here? So this is going to be the equivalence point, and I'll just maybe mark this one and then stop. Wow, that actually looks halfway decent. All right, so that's A. So this is the answer to A. Now let's go ahead and skip down to C, because C says pH equals pKa. Do you remember where that happens? Well, if you don't remember, it's where we're halfway to the equivalence point. So the easiest way to do this is just to kind of read down here to the x-axis, right about there. And it looks like we're at about 22. It's kind of hard to tell exactly, but I'd say it's about 22. Let's just say these are milliliters, so about 22 milliliters. So what would half of 22 be? Well, it would be 11 milliliters, so let's just go ahead and type in 11 here. Write in 11. So halfway to the equivalence point is going to be at 11, and the equivalence point is going to be at about 22. What about the region with maximum buffering? Well, I don't know if we specifically mentioned this, but it's this region that's flat right here, all the way from here after the start point, all the way across to about right about here would be the region with maximum buffering. So it would be about, let's just say 1 milliliter to about 20 or 21 milliliters. Okay, look at D. Where does the pH depend only on the concentration of HA? So think about that for a second, and then we'll answer. And the answer is when you first start off here at the very beginning, before you add any of your base. So in other words, where you only have HA, that's where the pH will only depend on that. What about E? Where does the pH only depend on the A- concentration? Do you remember this? It's at the equivalence point. And the reason it's at the equivalence point is because at the equivalence point, all of the weak acid has been eaten up by the weak base, and all the the strong base. And all the strong base has been eaten up by the weak acid. So there's not anything left except A-. In other words, the only thing that's left is what you produced when these two things up here were eating each other all up. And what they were producing was A- because the strong base here was plucking that proton off of HA and leaving us with this. So how would you figure out what the concentration of that is? Well, it's going to be the same as whatever the concentrations were. What you can do is you can actually figure it out. You have to figure out the number of moles that were added originally of the acid, and then at the equivalence point you'll have the same number of moles of the base. So that's how many moles you would have of the A-. And then to get the concentration, you would have to then divide that by whatever the total volume is, which you'd have to add the original volume of the acid to the volume of added base. And then F, the only one that we haven't done, the pH depends only on the amount of excess strong base that was added, and that's going to be anything after the equivalence point. Anything in that regime right there. Because at that point, here and beyond the equivalence point, what's happening is that you've added more base than you had originally of the acid. So the acid is all gone, and all you have left is some of this stuff right here. That, you're going to have some of that, but you're also going to now start to have OH-. And remember that we said in class that whenever you have the OH- and you also have this up here, that you just disregard this as far as finding the pH, because this is a very weak base, whereas this is a very strong base down here. So just use this one to find your pOH and then to find your pH. Moving to the next slide. Okay, so find the pH at the halfway point and at the equivalence point for each of the following titrations. At the halfway point, pH is going to be pKa. So let me just type this into my calculator. 6.4 times 10 to the minus fifth gives me a pKa of 4.19, and that's all you have to do. So there's your answer to A. Or anyway, that's the answer to the halfway point part. And notice you don't really have to worry about any of this other stuff over here. At the equivalence point, okay, so let's go ahead and do this. At the equivalence point, what you should do is start off by figuring out how many moles you had of whatever thing was in there to start with. In this case, we're titrating with NaOH, so that means that we were starting with this stuff right here. When you have 7 carbons in a row, that's called it's called heptane. When it's an acid, it's called heptanoic acid. So here, this is heptanoic acid. So when we first started off, we had 100 milliliters or 0.1 liter of the heptanoic acid, and it was 0.1 molar. So we had 0.1 liters, and we had, so I'm going to multiply this times 0.1 moles per liter, which means that we had 0.01 moles. Which means that when we get to the equivalence point, we have added 0.01 moles of the NaOH. Now, this is the number of moles of both. All right, at the equivalence point then, they've eaten actually the acid and the base have eaten each other all up, but in the process of doing that, so we had 0.01 moles of the acid originally, and then we had to have added the same number of moles of the base to get to the equivalence point. In the process of doing that, we would have also created this same amount of the, it's the heptanoate. So it's heptane, heptanoic acid, and then when you pluck a proton off of that, it's called heptanoate. In other words, it would just be this right here without that H in front of it, and with a minus charge. So that's this number right here would be how many moles we would have of that. And that's the only thing we have that has acid-base properties other than water, because the NaOH has been eaten up and the heptanoic acid has been eaten up, right? So what we have to do is find the concentration. So that's your stoichiometric part of your calculation. You figured out how many moles you have of this stuff up here, this stuff right here. So you want to know, do your ice table. But we don't want the number of moles of the heptanoate, we want the concentration. So we're going to have to divide this by the total volume. So can we figure out the total volume? Well, if we look back at the problem statement, the concentration of this weak acid was 0.1 molar, and the concentration of this strong base was 0.1 molar. So because their concentrations are the same, that means the volumes have to be the same. So that means that we also would have added 100 milliliters of the NaOH. So we started with 100 milliliters of the acid, and we added 100 milliliters of the base, so we have a total of 200 milliliters of solution. Or 0.2 liters. So what we have to do is divide this number of moles by 0.2 liters to get the concentration. So whatever we get for that will be the concentration. We'll make an ice table. So what do we write across the top of the ice table? Well, we write C7, and I'll try to just take a moment to do this. So C7H5O2. And it's going to have a minus charge. Is the only thing that we have left over. Okay, so we're going to have to put that somewhere at the beginning. So what I'm going to do is I'm going to write out this equation. It's going to end up over here somewhere. So what am I going to add to this? Well, we always add the same thing in this kind of a calculation, water. So let's add water, and then let's figure out what's going to happen if we add water to heptanoate. What will happen? Well, this minus charge will pluck a proton off of the water and reconstitute the heptanoic acid, which would be C7 with the H in front of it, and then H5O2. And then what's going to be left of the water? So while I agonize over this, why don't you think about that? What would be left of the water if we plucked a proton off of it? Well, it would be OH minus. So this is the reaction we need. Well, what's the K we need? Is it this right here? And the answer is no, because this right here would be what we would use if we had this thing written the other way around, this way. But we don't. So we have to use KB for this stuff right here. So how do we get that? We just take the KA. We need the KB. So we take the Ka value here, which would be for this stuff right here, and take 1 times 10 to the minus 14th divided by that value, which is 6.4 times 10 to the minus 5th, right? And whatever we get is going to be the KB. All right, so this is what goes across the top of your ice table here. So just write this across the top of your table. And then your initial concentration here will be whatever you get. Let me just actually do this so that we can write it in. So it's 0.01 moles divided by 0.2 liters, and that is 0.05. So 0.05 is what's going to be your initial concentration for this stuff right here, right? And then that's all we have. So everything over here is going to be 0 at the beginning. So this is the I part of it. I'm not going to have room to finish it, but we'll just do it verbally. And then this is going to be 0 also, approximately 0. All right, so just to go ahead and talk you through the rest of this here, 0.05 minus x, you know, the same spiel, 0 plus x is x and 0 plus x is x here. We wind up with x squared over 0.05 equals whatever we got for KB. So let me go ahead and flip now. So let's see what we did get. We got 1.56 times 10 to the minus 10th. Okay, so this right here, where I'm drawing this line back and forth, at the bottom is KB. That's what we got when we divided 1 times 10 to the minus 14th by 6.4 times 10 to the minus 5th. And it's going to equal x squared over 0.05. And that's the same thing we just said. So solve this for x. When you do that, you get this number right here, 2.79 times 10 to the minus 6. If you look back at your chart, which I can't do, you would look back up to see what does X stand for. Well, it stands for the OH minus concentration. So if you take minus the log of that, you'll get the POH. And so I did that, and the POH is 5.55. Then to get the pH, you just subtract 14 minus that 5.55. And you get your answer, which is 8.45. Now, actually, don't get discouraged if you're having a hard time with this problem. This is the hardest one for either if you're doing weak acid or weak base titrations. This is the hardest one because you have to do a lot of stuff, so it's a pain in the neck. But if you can do this one, the other ones are almost certainly going to be a little bit easier. Next slide. Here is the ice table. Next slide. All right, so we're going to skip this one completely. 1265, skip it. Next slide. Next slide. Multiple choices. I was going to go through these with you, but to be honest with you, I think that we've gone kind of like over our time limit. So what I'm going to do now is I'm going to just go ahead and go through the rest of these slides with you. I'll tell you when I'm getting ready to flip the slide. I just want to go through these to make sure that there's nothing else that we're not going to worry about. Otherwise, I'm going to just let you guys finish this off yourselves, but I think the rest of these are fairly straightforward. And I think that we've done the hardest ones. And I mean, I can't make these videos too long because, for one thing, you're not going to want to sit there and listen to it. You're just going to get sick of it and turn it off. So let's just go ahead. I'm just going to go ahead and start telling you. I'm going to flip, just to make sure there's nothing else in here that you don't need to worry about. I don't think there is, but let's just make sure. So I'm going to flip. I'm going to flip. This one's okay, so let's go ahead and go to the next one. And the next one. This one is okay. Next. Next. This one's okay. Next. Next. So I'm just going to start saying next, 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 because I think the rest of these are fine. Next. Next. I don't know how that got in there, but next. 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 Before we move past this one's a little tricky because it's hard to tell which one of these two things is the acid and which one is the base. So let's just stop for a second and look at this. Which one of these two things, this one or this one, has more H's? This one's hard to see. So which one do you think is the base and which one do you think is the acid? Well, this is the acid because it has 3 hydrogens. And this is the base because it only has 2. So what happens is this one here can accept a proton from this one. So this is actually a conjugate acid-base pair. It's a weak acid, weak base pair. So when you do this problem, you want to have the base over the acid to use the HH equation. This is just as we've done before, like I don't know how many times. So you'll put the concentration of this one on top. In other words, you'll put 1.1 on top and then put the concentration of this one on bottom. In other words, you'll have 0.35 on bottom. So your last term in your HH equation would be the log of 1.1 divided by 0.35. Okay, so, and other than that, you should be able to do this one. So let's go ahead and go to the, and here it is. You can see it down here also. Okay, next. 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 Okay, this one you don't have to worry about, but if you're pre-med, I would recommend that you at least look at this and try to get the highlights of it. But for number 25, as far as for the main class, you don't have to worry about this one, just skip it. Next. Next. And then this one is another one of these, it's after the equivalence point. So what's going to happen is you're going to wind up with more NaOH than you have acid. And what that means is that you just want to figure out how many moles of the acid do you have, or did you start with? How many moles of NaOH did you add ultimately? And then subtract this number here minus this number here, and that's going to give you the number of moles of excess NaOH. Excess NaOH. Once you have the number of moles of NaOH that's excess, you divide it by the total volume, which is going to be 50 milliliters plus 150 milliliters, which is 200 milliliters, or 0.2 liters. So 200 milliliters or 0.2 liters. So whatever number of moles you wound up with, divide it by this number right here, and that will give you the molarity of the NaOH. And then just take minus the log of that. That will give you the POH. Well, I won't write it here because we don't want minus the log of 0.2. Whatever we get when we divide by 0.2, take minus the log of that. That gives you the POH, and then just subtract that from 4 to get the pH. Okay, and then this last one, I think this is the last one. We're going to end up here with, again, we've added, notice, we started with 0.2 moles of the acetic acid, and we've added 0.03 moles of NaOH. So what's going to happen in this problem, just to look at it up front, there's less of this than there is of the acid, right? Considerably less. So what's going to happen? Well, the NaOH is going to run out, and it will eat up 0.03 moles of the acid, leaving 0.17 moles of the acid, none of the base, the strong base, right, because it's going to be eaten all up. But what's happening when you react NaOH with the CH3COH? Well, it's producing acetate. So you'll also wind up over here with 0.03 moles of acetate. So you have both. All right, so you would go ahead and you would set up your table the same way you always do. Your initial concentration of your acid will be this, and your initial concentration of the acetate will be this. So down at the bottom, in the, whatever you've got here, down at the bottom, you're going to have X here, 0.03 here, plus X, but we're, so 0.03 plus X, but we're going to disregard the plus X. And this is going to be 0.17 minus X, which we, again, will disregard the X. And so what are we going to end up with here? We're going to end up with K, which is here, equals 0.03 times X divided by 0.17. Solve for X, and you will have solved for whatever you have here. So what would we have here? Okay, do you remember? We're going to have H3O plus, right? Because what's going to happen is when we add water to the acid will protonate the water to make H3O plus. So this is over here, this is going to be your acetic acid, and this is going to be your acetate over here. So whatever you get for X, when you solve for X, that's going to be your H3O plus concentration. So once you take minus the log of that, you have the pH. Now I think, I'm going to flip the slide now, and I'm going to flip it again, and again, and this is the end of this thing. So what I'm going to do now is I'm going to go ahead and get out of this and post it on Canvas. If you have any questions at all about this, don't hesitate to email me. I'm glad to help you with it if I can. So that's going to wrap this up. Probably went a little too long. So this is going to wrap up everything that you'll need for the second exam. Having said that, for the second exam, please be sure to study really hard for it, because it's probably going to be difficult. So, I mean, I can always curve the grades, but I prefer that you just, go ahead and do your best and try to do well on it the way it is, because it'll be difficult, but you can do it. So just hang in there. And know this was a lot of problems, but anyway, hopefully by the time you get through with all this, you'll really understand titrations. All right, so that's going to wrap it up for Chapter 17A. We'll start Chapter 17B after you take your second exam and then move on from there.